Okay, so I think we should just get started. Welcome again to 2026, everyone. Um, Good to have you all here. My name is Olu Jonah, and I am the PI of CONGA. And we have today the privilege to host or to have our special speaker. He's also a member of CONGA. Now he's one of the leadership in this CONGA mission. And as you will see in his talk, he will highlight and outline some of the missions, some of the objectives and strategic objectives that we have for CONGA. So I will introduce him properly later on, and he will be talking about the strategic, let me see here, the steps in developing the data and processing software for CONGA GNSS receivers. So um, that is Dr. Giorgio Picanço, and I will hand over the podium to him in a short while. So I also want to welcome all our new members. We had a lot of them. I will show you the table. I put the names of people that have just joined us in the last 1 month in a table so that we can see and welcome them. I want you to feel free to ask questions and feel free to share your thoughts. So we have a lot of updates. Most of the updates will be given by by Dr. Picanço in his presentation. And also to let you know that Ms. Yenka will be attending the ICEA meeting in Liberia, Costa Rica, and will be presenting um, on CONGA objectives, and she also presented similar poster for um, Beacon Satellites the last time, I believe, and I was at AGU in December to also present some updates on CONGA. So this February 9, Ms. Yinka will also present the updates that we have, new updates for that matter. We have a lot of updates on CONGA. So we are excited to showcase the poster. And also, yeah, so for the meeting, please feel free to um, contact me if you have any presentation you want to give in the meeting. I will show us some of the tentative speakers for the next 6 months as well. So I know that we are always short on time, and this time around it will not be an exemption. So today, before we get started, I also want to let us know that this group of people joined us, and you can see they are balanced between students, um, researchers, professors, and other set of careers that we have here. So a lot of people are interested in the CONGA distribution over the equatorial region. And it's something that I have been asked a lot of questions about. Like when I was at AGU the last time, a lot of people walk up to me and say, oh, we need this CONGA mission to validate COSMIC 2. So that is essential, right? That is one of the essential things that we are excited about. And other questions that are asked, that are very prominent to CONGA manifestations or establishment. So we welcome all of these people from Kenya, Nigeria, USA, and Ethiopia is here, Uganda, Ghana, Benin, Cameroon. This is what we actually emphasize, and this is what this meeting is all about. My next slide shows that, we want to build a network of people that can work together. Work together in the sense that we want to accomplish this mission with everybody's hands on deck. So given that we have different people from different countries around that region, it's very essential. And outside that region, it's also welcome and it's essential because they gave us the backup that we need to move forward in this project. And also, as you know, this project, this meeting, CONGA meeting series or webinar, as you may want to call it, it's also about education. We are training people to, the kind of training and development for our member to be able to handle the instrument when the time comes. So this is an embryo, like it's an egg in an embryo and is getting incubated. And when it is hatched, we don't want to keep waiting on the side. We are already prepared to set all of these things in motion. So that is why this meeting is important. It's also important because of the data distribution that we normally want. Right now, like I said, people walk up to me and say, "What we have data in Africa. Some people have this data, but they are not opening to sharing it." So that is why also Conga is here. We want to share the data for science and other missions that are there, like survey and navigations and communication systems will benefit from all of these programs. So one of our mission is to make sure that distribution and accessibility of data are available across the board. So this morning, we are very privileged to have our own Picanço, Dr. Picanço. Dr. Picanço is a space scientist and is from Amazon region whose early curiosity about nature led into physics and space physics, which with research focus on ionospheric physics and space weather. He is currently a postdoctoral research associate at the U Max Lowell Space Science Laboratory on the Office of the Naval Research funded IDA project, where he helps recover, standardize, and integrate legacy in ionospheric data into global database used for near real-time ionospheric modeling. He also develops open source Python tools that combine ionospheric data with GNSS, LEO, and radio occultation observations to study storm-time ionospheric behavior. He has published 38 plus peer review papers, collaborate internationally, including groups in Brazil, Argentina, Mexico, Finland, and Germany, and enjoys playing Brazilian music such as Samba and Bossa Nova. So Dr. Picanço is a very good friend of mine. I remember the very first time I met him was in Brazil, and he was starting his master's at that time. He walked up to me and said, "Oh, Jonah, well, I like your paper on TEC variability over South Africa. I think we should collaborate in the future." So I remember that time like yesterday, and look at it today. We are collaborating. We are not only collaborating, we are also very close together here. Dr. Picanço is my very close neighbor across the street. So we meet every week to discuss Conga, even though we meet here every month. My Dr. Picanço and I, we meet every week because he's one of the important leadership in this Conga mission right now. So we meet every week to discuss the new way forward for Conga mission. As you know, there are so many challenges we have, but we have also so many solutions to those challenges. So this morning, I welcome Dr. Picanço to share his thoughts on Conga mission for us this morning. Dr. Picanço, please, the floor is yours.
Okay, hi everyone. Thank you, Jonah, for the kind words. It was meant to be. It's a pleasure to be here. It's a pleasure to present this first first contribution to Conga project. And the objective of this seminar today is just to present some of the work that I've been doing with the GNSS data processing, because as Jonah told us, I've been developing Python codes for GNSS data processing, open access codes, open access libraries. And the idea is to try to make this work to be close to the objectives of the Conga network, because in this case, we can use these techniques to better develop GNSS receivers, especially in the software part. So let me just share my screen, and I think we can start discussing about this topic. Okay, just a moment. Okay, just give me your confirmation that I can see my screen.
Yeah.
Okay, all right. Let me just hide this panel. Okay, so as Jonah told us, this is the title of my seminar, First Steps in Developing the Data Processing Software for the Conga GNSS Receivers. I really appreciate your presence here. I hope I can give a piece of contribution with this ongoing project. I'm very pleased for being invited by Jonah and the other Conga members to join this amazing project. Let me start by the context and motivation for this whole work, not only within the scope of the Conga, but within the scope of the work that I've been doing. That's just a continuation of the uh, amazing work that have been doing by professors in Brazil, just like Professor Eurico, who supervised Jonah. So this is all about the ionospheric response to space weather phenomena. Okay, we have here this ionized layer of the Earth atmosphere, a very responsive environment to everything which happens in the sun, and it's directed to the Earth. So here in this context, we have different eruptive and radiative processes working in the sun, like the coronal mass ejections and the solar wind acceleration and um, increase in pressure. All of these space weather forcing that can affect the magnetosphere and the thermosphere and also the ionosphere. And together with the solar flares and the other solar phenomena, all of these events, they can affect us here in the Earth, in Europe, or in the geospace by means of different effects that we can observe, like signal scintillation in the GNSS systems, or for example, radiation damage to satellites, astronaut radiation, and crew and passenger radiation, or increase in error and positioning error in these spacecrafts and the aircrafts too. For example, I don't want to be inside a airplane during a magnetic storm, because I know that this can create the capabilities and the performance of the GNSS uh, positioning system. So all of this is in the context of space weather, and I think it's really important to have really good methodologies to try to derive a proxy for the ionospheric response for these important events. And I think this is all the context and motivation for starting developing a good software in the scope of the Conga project. So just let me mark the time. I have about 4 minutes. You told me, right, Jonah?
Yes, sir. Yeah.
Okay, I will try to not extend it too much. So just like I said, GNSS preservation, they offer high temporal and spatial resolution, continuous global coverage, and freely accessible data for atmospheric studies. In the context of these GNSS data, the ionospheric indices, they are currently the like the hot topic of the atmospheric research, especially in the methodological part. So next year we'll complete like 30 years of the one of the most important, if not the most important indices. The ROTI, published by in P in quarters in 1997. And then we also have the DAX, published by Jakovsky. We also published with Clesio in Brazil, our own version of the DAX. And more recently, the TC anomaly by Nickel in quarters in 2024. So this relevance is further emphasized, for example, by COSPAR action teams, such as the G2B04, the atmospheric perturbations indices and the scales group. So it's important to mention that these indices, they serve as the essential tools for atmospheric monitoring, space weather research, and GNSS-based applications, as they provide us a single and easy to understand value of the atmospheric degree of perturbation. So as a matter of atmospheric variation, the indices, they are really good. And so DC, total electron content, is really good for long-term studies too. So this is um, prototype of the model prototype for the CONGA GNSS receiver that I've been discussing with Jonah. It's just um, uh, advance of the first model he proposed, but it's basically the same, just with different parts. But here, one thing that's important is that for this device, we need reliable software to operate this GNSS module. So an option is to use an onboard computer for both the sensor management and the data post-processing. Because once we can just include a computer able to process the data, not only collect it, but also process and deliver us like level 2 outputs, we can make it more independent to external products, external computers. So this is just an example of the onboard computer that can um, have think, can keep the data processing software and not only manage the sensor low-level acquisitions, but also deliver us second-level products like TC, ROTI, DIX, SIDX, and more. So as a part of the motivation, we know that we face major challenges. For example, one of them is that we have really good softwares for data processing, but most of them, they are black boxes. We see that they have like proprietary algorithms. We can enter with our data input and we can get the data output, but we don't know what's happening inside. We just need to trust them. So in this case, I think this is something we can address without Python based software that will be evaluated and accessible to all the community. Also, we had this problem of the costs because we really have good software that has the source code available that is open access for those who pay. So if you have, for example, $1,000, you can buy a good software for GNSS data processing. This is not good for the community because sometimes we are trying to focus on our research on low cost instruments and low cost techniques. So if I have a low cost GNSS receiver, doesn't make sense to have a high cost software. And sometimes we also face the lack of reproducibility, because when you see these new indices, these really nice, colorful maps, GNSS, atmospheric maps, we want to reproduce it, but most of them, they are difficult to reproduce. And we also face this famous sentence on the papers, data available upon request via email. We know, we all know that this data will not be available. So to try to address this problem, I think we need to focus on these three requirements. So first of all, let me introduce this idea of the GNSS systems. I know that here I'm among specialists, but it's never enough to talk a bit more about the components of the GNSS systems. So here we have, for example, the satellites. It can be like a GPS, American GPS, GLONASS, Galileo from Europe. So of these satellites, they will transmit signals in different frequencies. So based on these frequencies, that will be, for example, cellular range in two frequencies, 2 or 3 frequencies, or phase of the carrier of the I mean carrier phase measurements in 2 or 3 different frequencies. We can mathematically compare these frequencies, these signals, and keep only the part that varies with plasma, which is the TC. So this is a really good um, methodology for studying the ionosphere, because we know that the GNSS systems, they are originally developed for positioning and navigation. But as we have the ionosphere and these signals are transatmospheric signals, so we can use it to study the ionosphere. For example, with GNSS observations, we can extract very valuable information about the ionosphere, okay? And then I show here just an example of the code global ionospheric map. This is for October 19, 2014. So more satellites are tracked, the greater the data coverage. We know that. And the more ground stations are available, the higher the spatial resolution. This is the whole scope of the CONGA project, as of my understanding. So the more signals pairs are received, the richer the data set becomes. So in short, more is more. In this case, there's always room for more data, because we need to cover all these regions that uncovered. So here I show just an example of what we can do with the same data. Here I have the same stations, the same epoch, the same GNSS data, and 2 indices. DIX showing this asymmetric disturbance. I know this is an uplift of the F region ionospheric drift. And at the same time, I have the result of this uplift, plasma bubbles being observed on the ROTI index. So with the same data, we can understand different features of the ionosphere. So this is why it's so important to have this data. So for this, there's our proposal for that. There's a library that I've been working with. I've been developing since November 2023. I called it Oasis. It's the open access system for atmospheric studies. It's all available in my GitHub. People can just go there and download this data and use it. So it's developed entirely in Python using the standard scientific libraries. It deals with the automatic detection of psychosleeps, outliers, and data gaps. It performs arc-wise geometry leveling of carrier phase measurements. It's independent of external products like DCVs or global TC maps. And I like to repeat this, it's independent of external products. So we just need to drop RINEX files or low-level sensor data that comes from the GNSS module in the context of the CONGA receivers and the orbits, satellite orbits, and will deliver us these. Actually, there are not only 3, but 4 parameters. TC, following the approach by Dr. Amalia Mesa in the National University of La Plata, Argentina. ROTI by P and Coulters, 1997. The TC anomaly by Nickel and Coulters, 2024. And the SIDX is an index proposed by Professor Norbert Jakowski in the DLR in Neustrelitz, Germany. So the input for the OASIS is RINEX version 2 or 3 observation files and the SP3 precise orbit files. It's compatible with GPS in GLONASS so far, because we are working the Galileo and Beidou for the next updates. Okay, so this is the structure of the OASIS. In the context of the GNSS device for the CONGA project, I made some modification on this structure. First of all, we start with GNSS module, and we get carrier phase and pseudo range observations. These carrier phase and pseudo range observations, we use it to construct RIMEX files, version 2 or 3 with 15 seconds or 30 seconds. Of course, this is something just initial. We need to decide what's the better format for this kind of data. So this data can be available into the database, local storage, and cloud. So from the same carrier phase and pseudo range observations, we also include data from the orbit files that are provided by different data services like the COLD, IGS, NASA. We use this collection of data to compute the Melbourne-Hubina combination. I will talk more about it in the next slides. We perform the arc segmentation. This stage is to deal with anomalies in the data. So just to improve my capabilities in detecting these anomalies without having to look for it into each individual data series, we compute these combinations, and then we look for cycle slips and outliers. We have an initial screening and the final screening for these cycle slips and outliers. Once no cycle slips or outliers are detected, we just go to the geometry-free leveling or carry to code leveling, as we can also find literature. And the last stage of the computation is to obtain the TC and the indices. And then we calculate the ROTI, SIDX, and DTAC. We save the outputs, and we also upload it to the cloud or to the storage, local storage. And then the pipeline reaches to the end. So the Melbourne-Hubina combination, it's integration of it's a combination of three main elements. The frequencies of the carrier waves, in this case in hertz. For example, we have here a table with the current used bench pair from the GPS in GLONASS system. We have L1 and L2 and L1 and L5 from GPS, L1 and L2, L1 and L3 from GLONASS. So this A or B in this equation can be 1 or 2 or 1 or 5 or 1 or 2 or 1 or 3. So we take the carrier frequencies and the carrier phase measurements in meters. We just convert them using the wavelength, and also the pseudo range code measurements. So it will combine these parameters. So we have a single data series in which we can screen for anomalies, for psychosleeps and outliers. So using these criteria, we can define the psychosleeps and the outliers. For example, we just calculated the difference between the Melbourne-Hubina and the previous value for each value. We fit polynomial function of third degree, and the residuals will be the absolute value with the observed and modeled difference of these Melbourne-Hubina difference of this Melbourne-Hubina combination. So the interquartile range will provide us the difference between the third quartile and the first quartile. The residual that fall within this condition, they are psychosleeps. The residual that fall within this condition, they are outliers. So this is just an example of this process. It should be said that this Melbourne-Hubina is scaled before any kind of computation between -10 and 10, just to put it in a reference scale. Okay, so of these data we are processing here, they will not be used to calculate the TEC and the other indices. We are just looking for the anomalies. So in this case, we define the anomalies, and once we find these anomalies, we have the indices for the arcs, the data arcs. So for example, here we have this data arc, first data arc, second data arc, third data arc, fourth one. And then once we have this, we can just perform the leveling of this data, considering only the data arc without mixing noisy data with good ones. So we see here that even if we find these anomalies that are in red, we still have scattered data here. So of course, it would be necessary to perform the refined screening. So in this case, we just do the very same procedure, but without the scaling the Melbourne-Hubina and without using the absolute values of the residuals. So just follow the very same procedure, but no scale between -10 and 10, and no absolute value for the residuals, just this difference here. So with more strict thresholds, we define the psychosleeps in this way, and the outliers will be these criteria for the residuals here. So with this refined procedure, we can start the leveling of the data. We already have the indices for the data arcs, so we calculate the geometry-free combination for the carrier phase measurements and for the pseudo ranges. So this will be the equation for the leveling, and this will be the average of the difference between the geometry-free combination for the phase and the geometry-free combination for the pseudo range. And this time window will be the time window for the data arc. So we don't use a fixed time window. For example, if we have a data arc of 15 minutes, we use an average of 15 minutes. If this data arc is 3 hours, this will be our time window for this average. So this is an example of the data, the geometry-free combination before and after leveling. What's interesting here is that the geometry-free, something we can call it like the slant TC methods, because this is the relative levelet slant TC, not calibrated but levelet within every satellite. It's levelet related to the same satellites. I mean, it's not calibrated to with reference to a common model, but we can do that as a next step. But from this geometry combination, we can already calculate, for example, the ROTI, the DTC, the DTC. Even if we don't have the calibrated values, because we are dealing with the variation of the DC here. So we take this geometry combination. It's proportional to this length total electron content. I mean the relative total electron content level at 1. And we calculate the ROTI, the delta TC, the SIDX, and the TC. So this is the equation for the ROTI. We are all use it to this equation, but in this case, we are not using the STC here, length TC, but the geometry-free combination. And for these Bates pairs, we calculate the ROT and the ROTI, and we are working on including the Galileo and Beidou. This is just an example of the ROTI calculated for the Brazilian station Boa Vista. The day of year 49 of the year 2023. And here we have the ROTI for GPS L1, L2, GPS L1, L5, and GLONASS L1, L3. Sorry, L1, L2. This should be L1. Sorry, it's not L2, L3 because we just use the bench pairs that are in the table. So this is the ROTI. We can see here that we observe we have a really clean data series, because when we take a look on the daily on the daytime values, we don't have anything above around 0.3 or 4. But these scattered values here, they are related to plasma bubbles, irregularities, and believe me, because I study at this event, I don't know that there are plasma bubbles. I saw it on the all sky cameras. For the TC anomaly, we can also just use a custom version of the equation proposed by Nickel. Just replacing the TC with the geometry-free combination here. And then we have this kind of data here. This is the delta TC. It's really good to study positive and negative variations of the atmosphere that are related to wave-like structures like TIDs and LSTIDs. This is an American station for the May 2024 magnetic storm. And so the SIDX is a really good index proposed by Dr. Jakovic in 2019. This is an average of the route calculated over the geometry combination. And this is 1 minute average. And we can see here for this variation, milli TC units per second, the ionospheric response to 2 solar flares during the magnetic storm of September 7, 2017. And for the TC, we follow the approach proposed by Dr. Amalia Mesa in Argentina. We have this background atmospheric model, and we model it as a function of time, latitude, and longitude. And with this modeled background atmospheric model, we calculate the difference between this model and the geometry combination. This term here is something we call the DCB or the IFB. And once we have it, this difference between the expected atmospheric model, background model, we can use it to calibrate every series of geometry combination. Then we have the calibrated STC, and the VTC, the calibrated VTAC, will be the STC multiplied by mapping function, just to take the vectors of the line of sight between satellite and receiver and make them to have the same length. This is the VTAC, right? So this is just an example of the STC and VTAC that we can calculate using the OASIS here is rating SIDX. I'm sorry, it's not SIDX, it's VTEC. It's VTEC for the Porto Velho station in Brazil. This is the STC. This is the VTEC, and these are the coordinates of the ionospheric pierce point calculated using the same software. So here are some data output examples from the Oasis. Here we have a mood index analysis during the Mortgage storm. Have here for three Brazilian stations, the ROTI, Delta TC, and the SIDX. Here, amazing. We see amazing plasma bubbles signatures during the St. Patrick's Day magnetic storm. This case was making a test with GPS GLONASS in Galileo 2. We have a really good improvement on the resolution of these bubbles. And here we see plasma bubbles during the October 10, 2024 magnetic storm that developed and also reached the United States latitudes. Okay, just another example for the magnetic storm that just happened in November 12, 2025. This is all calculated using the Oasis. So here we see different signatures of these plasma bubbles. And this event was very interesting because it generated these mid-latitude super bubbles that assumed this reversed C-shaped morphology. I'm showing this because at the end of the day, it's all about science, right? It's not only about GNSS data processing. We want to use it for our research papers, for our applications to the society, to the scientific community. As I showed it to you, the SIDX response to these two solar flares, and the some TC maps that I just calculated only for this presentation. I'm using just 250 GNSS stations here, but we have more than 5,000 or 6,000 GNSS stations all around the world. So I hope with the CONGA project we can increase this coverage over Africa. But we already have the good software to start processing this data, and all this software can easily go inside this onboard computer of the GNSS device. Okay, so this is the address for this is a link for accessing the Oasis. It's all available on my GitHub, or can be used from the PIV install PyOasis, or just through this QR code. Okay, this is all. Thank you for your time, and I hope I didn't pass on my time.
Oh, sorry, I was muted. Yeah, thank you, Jorginho. This is good. This is really awesome presentation. And yeah, do we have any questions uh, before we continue? I know we have a lot of experts on TC, GNSS in the house. If you have any questions regarding this software process of processing, I think Giorgio has been doing this for a while. This is also part of his PhD, and he's also working at the Max Lowell to upgrade their process and also consolidate that with the ionosonde system that they have there. So if you have questions for Giorgio, okay, I think I have a hand up here. Francis, do you want to ask a question?
Please, I want to find out if aside the software, there will be any training, hands-on training
Oh, okay. So I think I was thinking about that when Dr. Picasso was presenting. I was like, okay, we're going to invite him again to actually give more detail from start to finish of TEC computation from GNSS RINES files. So maybe in the future we are going to invite Dr. Picasso to come again and give us a more detailed breakdown of this. Because here we educate, and there are a lot of students that are learning. Professors are also interested in bringing their students on this platform. So hopefully, we will invite you if you don't mind, Dr. Picasso.
Okay, no problem. Of course, I'm always ready to contribute.
Okay, so I think we have Ojo Boss.
Thank you very much.
Yeah, sure. Ojo, could you please ask your question? I think your volume is low. Can you bring it up a little bit?
Now,
It's better, yeah.
how's the volume now?
Yes, go ahead.
Okay. Hello everyone. My question is on availability of this software for use, especially for say an ordinary survey, not mainly for research. Can it be because you know this ionospheric uh, uh, effect on genetic positioning is very volatile, especially like Uganda, where we are around the equator, and there are many errors that can arise from the ionosphere. Can the secondary surveillance or can this be deployed for a surveyor to manage his or her work? And
Yeah,
then my other question is, I told them it is compatible with the RENX 2 and RENX 3, but we now have RENX 4. Are we going to adjust the software to cover RENX 4 in due course? It didn't plan to copy RENX 4 as well because we know the more advanced version of the button version, the better someone can manipulate and use it. So these are my two questions. I hope they were clear. Thank you.
Oh,
Ojo Boss, I think, Jorginho, do you grab
I
something?
I I apologize, but it was really difficult, Ojolos, to understand because I just listen like fragmented parts. The audio is not so clear. Can you write it, please? Can you type it?
Yeah, please, if you could type the question, the specific questions,
Mhm.
it will be helpful.
Okay, yeah, because the sound was not so clear.
Okay, so I
Can
think
type it,
it's
it would be nice.
okay. So why Ojo Bob's type his question? Is there any other question here at home in the house? And thank you, Dr. Picasso, for sharing your software. That is really good. People can also
Uh-huh.
use that to process their writings files. If they have any question, they will
Yes, and
definitely.
I invite the community to help me to improve it, to point to the parts that can be improved, and to any kind of problem that you can have using this software. I mean, it's our software because now I just released it to the community, and I think there's a lot of application that we can do with that. All my recent two papers, I use it to assist for the data processing. And so it's all for open access. It has open access in its name, right? Open access system for atmospheric studies.
Mhm. Okay. So, is there any other question? Uh, Okay, I think you have the question in the chat.
Can an ordinary surveyor deploy this WASI software for data analysis to improve his or her positioning accuracy, especially here in Uganda or generally places around the equatorial regions, to improve the positioning accuracy? Well, at first moment, I was more focused on the ionospheric study, the study of the ionosphere, plasma bubbles, quaternary ionization anomaly. I'm not an expert in positioning, but I do know that a lot of geodesy scientists, they use total electron content mapped for improving in positioning, the performance of positioning techniques. So I think if you want to take a look on the maybe Google Scholar, you just can look for something related to TC, um, calibrated TC for positioning systems.
Yeah, I think if you can calculate the error at the given time or the delay of the GNSS satellite signal, which OICs can help you to do, you can estimate the delay in the positioning, or you can calculate, you can improve your positioning in that regards. And I think that is what a lot of aviation system and communication system use that for. So I think there's a
Okay,
second question there.
second question. This is the this is the problem facing right now. He says, I saw that Waze handles only Rhinox 2 or 3. How about Rhinox 4? Are there any plans to advance the software? Yes. The Waze uses the GeoRhinox library, and it says the GeoRhinox library on the main page. It says that it process data from 2 and 3 versions. It's not the true. It doesn't handle in a good way the three Oranix 3 versions. So what I'm preparing for the next update is to stop using the GeoRhinox, and I will move to another code for opening the Rhinox 2, 3, and 4. I mean, Claudio Cesaroni from the ING has a really good code for that. The name of the library is something like PyTC. I need to remember. And so he presented it in the last Beacon Satellite Symposium, and it's really good for the Franex opening of 2 and 3 and probably 4 versions. So the idea is to try to assimilate these code into the Oasis as a module for GNS for Rhinox opening. Okay. It's really interesting presentation. Thank you very much. Thank you. What's the unique advantage of this software from other calibration software like OP and or use it currently? This is a trap question. I need to be careful. The advantage, I never compare it. The calibration software with the one by GoP and the other. What I can say is that if I'm not wrong, and I don't know if I'm wrong, but the software by GoP, it doesn't calibrate the DC. It downloads the DCBs from the code. And in this case, we don't need to download any type of DCB because we model the background ionosphere. So the advantage of this software is because you can do whatever you want to do with this, because you can open the code, you can check the code, you can see, you can compare. And for the indices computation, you don't need external products like DCBs. So in this case, I can't say that the TC from this software is good, it's better or worse than other software because I didn't compare it yet. I just finished this calibration methodology, calibration module in September? No, November for the Beacon Satellite Symposium. But I will do it in the future. But the advantage for this software is because we don't need to use external products, and I'm pretty sure, if I'm not wrong, that the software by Copy, it downloads the DCBs from the code. Yeah, maybe Dr. Cesar Valadares, who is here, he can talk a bit more about that. And yeah, there's more follow-up. Plans for validation against existing tools, methods, plans to implement unit tests in your Python code to ensure that it still runs as intended on the supported systems. Okay, the first part, yes, we will prepare a paper, actually a companion paper to present all the methodology of the OASIS this year. And the second one will be a case study using the most ionospheric parameters we can use for analyzing space weather events. And this topic of implementing unit tests on the Python code to ensure it still runs as intended on the supported systems. This is something I think that it changes from case to case. Once we define the hardware for the CONGA GNSS receivers, we need to adapt it to the software to this hardware. For example, the OASIS, the library, Python library, it's 100% Python. But if you want to use it as in a more institutional way, I would say that you need to define what is your proposal. For example, here at the UML Space Science Laboratory, we are trying to develop these global TC maps, but we don't use only Python for that because we still can use like a Bash Linux language to manage these Python codes to perform a parallel processing much better than only with Python. Python is not it's a really good language, but it's not the one that can resolve everything. So I think it really depends on the application you want to use it for.
Awesome. Thank you, Giorgio, for taking those questions and clarifications. And let me share my. Can you stop sharing your screen? Let me just share my screen a little bit. Oh, I think somebody's just joining us. We're about to finish here. But it's okay to join us anytime you want. So yeah, just to thank our speaker again for today. It's wonderful to have Giorgio talk about the necessary steps and the software that we are considering for CONGA in the future. There are some challenges as has been noted by the questions, validations, and all of those things will be coming in the coming months. We will try to work on those. And then when the time comes, we are also looking at the possibility to incorporate this in the or integrate this into the CONGA hardware. And we will also be working on the CONGA hardware. Myself and Giorgio, we are working on the side to build a systematic process to allow us to get started on the building of hardware, at least a representative hardware that we can say this is the hardware for CONGA. So we are working on that as well, and as well as the software aspect of it. So thank you very much again, Dr. Picanço. We appreciate your time today. And on next month, we're going to have a similar presentation about application, space weather applications, and that is going to be given by Dr. Frank Shingarandi. He's also from Brazil, INPE, and he's going to be talking about some of his work has to do with space weather and irregularities. So this is application to ionospheric instrumentation of GNSS receivers. So we are very optimistic, right? I would say with all of these, our speakers for the next 6 to 7 months. This is really wonderful speakers, right? We're going to have but today. These are tentative speakers, though. I need to still contact them and have their agreement on this. So these are beautiful speakers to educate us on some of these things that we need to add to our knowledge. And with that, is there any other question that is missing or something that we have not said that need to be said? Please feel free to take the floor. I'm still admitting people to join us. Okay. Let's see. Going 1, going 2, and going 3. So thank you all again and welcome to the new year. Somebody is saying Happy New Year over there in the text message. We welcome you to the new year and we hope that everything you do this year is going to be wonderful and CONGA is going to be a little bit better than last year, or so that we see that we are moving forward. Although we are always moving forward because we are educating people. So that is part of CONGA. Particularly this meeting. So it's part of education. So once we are able to do that, we are fine. But as part of the hardware, we want to also see some progress in that. So I'm positive that we are going to get to that this year. So thank you all again for joining this meeting, and we will see you next month by God's grace.
Thank you, Jonah. It was a pleasure to be with you. I just send my email here in the chat for the ones who want to be in touch with me. Thank you, everyone. It was a really nice time and talking to you. All right.
Yeah, I will put this on our YouTube channel, but our website is currently facing some challenges, but we're going to resolve it. But this will be go on into our YouTube channel for educational purpose.
Okay.
All right. Thank
All
you
right.
all. Yeah.
See you. Bye. Thank you.
Yeah. Bye-bye.
Bye.
Bye.